This is my second video in evaluating limits, but specifically limits that fail when you try to evaluate using what we call direct substitution, okay, which is the primary method for evaluating limits. That is if we were to, for instance, take a look at this limit right here, we say the limit as x is getting really close to 0 of this function here. What are its y values getting close to as x gets really close to 0? If we were to attempt to plug this in for every instance of x in this expression, we can see here that we would produce this new expression where we would get 0, 0, plus 1 in here, minus 1, this all over 0. And essentially what we get is this. We get root 1 minus 1 over 0, which basically produces 0 over 0. And we've referred to this as indeterminate form, okay? So the techniques that we're exploring here are kind of workarounds to find limits for things that algebraically don't exist at certain x values, but certainly do have limits or things that they're getting close to as x gets close to that value, okay? So this second technique that we're going to explore in this video is called the rationalizing technique, okay? Before we kind of get into the nitty-gritty of the rationalizing technique, I do want to find this limit, and I want to support my response with a graph and a table of functions. So the first thing we're actually going to do is look at the graph of this function and then produce a table of values to kind of come up with an idea of what we think the limit of this might be. So I'll pop over here to GeoGebra. You'll notice that you can see up here on the left, I've already input the function value here, and it's in red. We say f of x is this function right here. We can see if we were to just observe this function, we say as x is getting really close to 0, what are the y values of this function approaching from the left and from the right? And we can see that it looks like they're getting arbitrarily close to a height of about a half. And we could just further justify this if we kind of zoom in. There was a good view. We can see as x is getting really close to 0, we can see that our y values are approaching a height of a half. Now you'll notice that I said it doesn't exist when x equals 0. We see that clearly when we plugged in the value of 0, and we can just further go to show if I were to drop, say, a point on this graph and then kind of shimmy this point around, and we say as it approaches 0 here, it should actually pop out. It should not exist exactly at 0. So I don't know why my graph doesn't want to get rid of it here. Maybe if I zoom out. I got it to disappear earlier when I hovered it over 0. But I tell you what, actually to further kind of justify our point that we think it doesn't exist at 0, but it has a limit of a half when x approaches 0, what we'll do is we'll make a table of values over here. And so since the limit we're trying to find is the limit of this function as x approaches 0, what we'll do is we'll go ahead and put 0 in the middle of our table, and we'll go a few decimal places back from this. So back from 0, we'd have like negative 0.9. This would be negative, negative 0.1. This would be negative 0.2, and perhaps negative 0.3. And then coming up from this, we say 0.1, 0.2, 0.3. And what we'll do is we'll find the function values at these given x values. And so how I'll do this is I'll go ahead and type in f of, and then we'll plug in f of negative 0.03. But here's what I'll do. I'll type in f of whatever's sitting in cell A1 here, and that happens to be negative 0.03, and enter. And it says, okay, well, if you were to plug in an x value of negative 0.3 into this function, you would be right here at a height of about 0.54, so just a shade above a half. And if I click and drag this formula all the way down, what we see here is this. We can clearly see that as my x values are zeroing in on, no pun intended, 0, they're getting close to 0, we can see that the y values are approaching a height of a half, but at 0 it doesn't exist. That doesn't matter, however, because all we're looking for is what is it getting close to as x is getting arbitrarily close to 0 in this case. It's getting close to a height of a half. So going back over to this piece of paper here, this canvas, I mentioned that I didn't want to get into the details too much, but we said I wanted to find the limit of this, and it seems that we've discovered that the limit of this, let me get rid of those, limit of this is a half, a height of a half, okay? So now the question becomes, how could we have done this algebraically? Because we already see that if we try to direct substitute with this, what's going to happen is that we're going to get indeterminate form, this 0 over 0. So this rationalization technique, you can usually recognize that you need to use it because we have what we call a difference quotient here, but essentially we have a square root involved, okay? So I mentioned up here, I say another way to find limits of some functions is to rationalize the numerator of the function or the denominator. But I say this is essentially forcing a difference of squares upon either the top or the bottom of the fraction. What I mean by this essentially is this. We say that rationalizing numerators or denominators means to multiply the top or the bottom of the fraction by the conjugate of the bottom or top. You notice I switched the order around here, top, bottom, top. Basically, we're going to take both parts of this fraction times the conjugate of one of them. Okay, and when we refer to conjugates, recall that if we have some binomial expression like a plus b, or in this case, square root of x plus 1 minus 1, its conjugate would be this value here, a minus b, this other binomial. And the nice thing about multiplying by conjugate pairs is if we were to do the entire expansion here, we'd get a squared minus ab plus ab, and this would be minus b squared, where our middle terms would cancel out, but we would get this expression that has to be a difference of two squares. And in the case that we're dealing with right here, which is the square root of x plus 1 minus 1, we could say that the square root of x plus 1, this would have been like our a term in this scheme. So x plus 1. And then our b term would have been this 1 right here. We would have had 1 and 1. We would have had plus 1 minus 1, respectively. And if we had multiplied this out, we would have gotten just this, a squared minus b squared, where our a, again, was this, square root of x plus 1, and our b was 1. And the nice thing about this is when you square a square root right here, what you get left with is this, just x plus 1, and we're taking away 1. And in this case, if we combine like terms, we even get the 1's to drop out, so we just get x, which is what we were attempting to do in the first place. So, to do the rationalizing technique, let's go ahead and use what we know about differences of squares and conjugate pairs. We are going to take this limit. We say the limit as x is getting arbitrarily close to 0 of this expression right here, x plus 1 minus 1 all over x. Direct substitution fails, so what we'll do is this. We will take this expression and we will multiply the top and the bottom of it by the conjugate, in this case of the numerator. And we said the conjugate of the numerator is square root of x plus 1 plus 1. And we have to do what we do to the top also to the bottom. So we get the square root of x plus 1 plus 1. And so we get this new expression where we're still taking the limit of it. We say the limit as x goes to 0. But on the top here, we notice that we're going to have produced a difference of two squares, where we're going to get, I'll write this out the long way the first time. We get the square root of x plus 1 squared minus, it's a difference of two squares, minus 1 squared. And this is all over. Now, the bottom, I'm going to make a recommendation here. Do not distribute on the bottom. Go ahead and leave this factored. The reason why we'll see in just a moment. But going ahead and rewriting this again, we say this is all just the limit as x approaches 0 of this expression here. Now on the top, if we were to square the x squared plus 1, we'd have x plus 1. And if we were to square the 1 here, we say square that 1 is 1. We notice that the 1's cancel out, and I'm left with just x. And on the bottom, we still have this quantity, a lot of rewriting, not a huge deal, plus 1. But essentially we get left with this. We get left with the limit as x goes to 0, or gets really close to 0, of just this. We had x on top. On the bottom we have an x times the quantity, the square root of x plus 1 minus 1. And the beautiful thing about this is now we have x over x times something. And so since the bottom's a product, we can cancel out these x's. And so now we're left with this. We have the limit as x goes to 0 of this, 1 over the square root of x plus 1, that minus 1. So why we wanted to arrive at this in the first place is because we now have the capability of direct substituting into this expression. Okay, so if we were to directly substitute in this 0, put a 0 in right here, we would get this 1 over the square root of basically 1 minus 1. Okay, so we'd say that 1 over the square root of 1, pardon me, this is a plus down here. I was like, wait a minute, we'll get undefined. But essentially, we'd get the square root of 1 plus 1 in the basement. And so direct substituting, we just get this. We get the square root of 1 plus 1 is 2. We get a half. And so we were able to evaluate this limit algebraically. So I don't know, what's the question here? I guess the question would be, what's easier, to look at the graph or the table, or to evaluate this with a rationalization technique? And I'll tell you what, most of the time you're not going to have a graphing utility or a Microsoft Excel next to you to produce these types of resources, so we have to be able to do this algebraically. So really quickly, I just want to do this one more time with this quantity right here. Okay, so let me kind of readjust some things here. I'm going to click on this. Maybe, possibly. Well, it doesn't want me to bring it to the front. So I can't write on this little white portion, but oh well. I notice that if I direct substitute this 0 in right here, just mentally, what I'm going to get is this. I'm going to get the square root of 9 minus 3 over 0. And in other words, I'm going to get 3 minus 3 over 0. Or here's our indeterminate form. So in an instance where we wind up with indeterminate form, we're going to have to actually go ahead and use one of our techniques, either dividing out or rationalizing. And since I see that I have a binomial on top, I'm going to rationalize. So a lot of rewriting is about to begin. But we say the limit as x goes to 0 of this expression, square root of x plus 9 minus 3 over x. We're going to take this on top and bottom times the square root of x plus 9 plus 3. Okay, that is the conjugate of our numerator. Okay, so plus 9 plus 3. And so on the top, what we get is this instead. We say the limit as x goes to 0 of a difference of two squares, where if we were to square now x plus 9, we would get this. We would say just simply x plus 9. And this is minus now the square of the second thing, which is 3 squared. It's 9. And we said this is all over. Now we don't want to go ahead and distribute this, but x plus 9 is in this radical here. This is plus a 3. And so what we get on top is this. Furthermore, we're going to be left with just an x on top, and that x on top cancels out with the x on bottom. So now this expression has just instantaneously switched into this, the limit as x goes to 0 of just a 1 over this quantity here, x plus 9 plus 3. And so if we were to actually now direct substitute, which we're able to do and get a defined value, we could say this would come out to be 1 over the square root of 9 plus 3. Which the square root of 9 plus 3 is actually 3 plus 3, so we get 1/6. Okay, and just to observe this, I do actually want to see before we finish up this video, but if we were to say click off the last function that we had and get rid of this point here, and put in this new function, you can see that this function is kind of flat. But we say as x approaches 0, if we zoom in here, is it approaching a height of about a sixth, which is about 16% of the way up? And you can see that, yeah, it actually is. And even up here on the table, if we were to type in G of cell A1, and then copy this formula all the way down, we see that, of course, it doesn't exist when x equals 0, but it's getting really close to a height of 0.1666666. So this rationalization technique is very, very nifty when we're dealing with instances that dividing out doesn't work, but we still wind up with indeterminate form. Cheers.